In this lecture, we're going to look at how to use transition matrices to solve problems involving Markov chains. We'll talk about what a Markov chain is in a minute, but first let's recap some of the facts we've seen about stochastic matrices. So the definition of a stochastic matrix is it's one where if you add up the column sums, they all sum to 1. So if this matrix M here represents 3 different possibilities or 3 states or 3 bins that you can be in, say A, B, and C, then one interpretation of this matrix is it gives us the probability that we would move from one bin to another. So if we're already in bin A, that would place us in the first column. We would move to bin A, or rather we would stay in bin A, at a probability of 63%, or 0.63. We would move to B with probability 15%, and we would move to C with probability 22%. You can repeat that calculation for the second and third columns. One property we saw is that there's always a vector, I called it U, whose entries sum to 1 and which is fixed by the action of this matrix. In other words, if I take this matrix and I multiply it onto the vector U, I just get back U. Then we talked about the fact that if M is not only a stochastic matrix, but it's also what we call a positive stochastic matrix, meaning all of the entries are greater than 0. Then if you take M and you exponentiate it to higher and higher powers, you'll see a sort of convergence take shape where every column turns into that vector U. So it looks like the single vector U repeated in each column. Now really that convergence might happen in the limit as n goes to infinity, but in practice what we can do is work in Matlab, take the matrix M and just raise it to something like the 300 power or the 10,000 power, and if this convergence is going to happen, we should observe it at that point. Another feature that we discussed is that once you've got M in this form, or in other words, once you've figured out what the vector U looks like, then U contains what you could think of as like the long-term probabilities of being in a particular state. Okay, so we're going to keep working with these ideas in this lecture. We're just going to look at more problems. Let's start with one where we're going to get a positive stochastic matrix. I didn't want to get too political here, so I just invented 3 political parties, A, B, and C. And this kind of data does exist, say, in our political system. So you can say, all right, if you voted Democratic last time, what's the chances that you're going to go Republican or Libertarian or something like that? I just made up these numbers for these 3 political parties, A, B, and C, so they don't correspond to any known political parties. But let's say that someone who voted for A last time, say Party A's candidate, is 82% likely to stay with A for the next election, 10% likely to switch to B, and 8% likely to switch to C. So that adds up to 100%. We don't have any other political parties, and we're also assuming that they're not going to not vote. Okay, then someone who voted for B last time is 86% likely to stay with B, 2% likely to switch to A, and 12% likely to switch to C. If you voted for C last time, then you're 80% likely to stay with C, 14% likely to switch to A, and 6% likely to switch to B. Okay, so suppose in the last election, 80,000 people voted for the Party A candidate, 70,000 for the Party B candidate, and 50,000 for the Party C candidate. Assuming we're just going for largest number, that would mean that A would have won the last election. Now for the rest of this problem, we could say, just imagine we look only at the people who voted last time and they're going to vote again. What I wrote here is that assuming no voters will start or stop voting before the next election, so we're not going to introduce in any brand new 18-year-olds nor have anyone decide not to vote, just sticking with these 200,000 voters, who's going to win the next election? What about the election after that? Can we make any long-term prediction which in this context might not be very useful if we were actually studying election data, because long-term you would certainly want to include the effects of new voters as well as people who stop voting. Okay, so let's set up our matrix on paper and then we'll switch into Matlab. This is going to be a 3x3 matrix. Instead of working with bins, we're thinking of the political parties as our locations. So if you voted A last time, Then we'll fill out the first column by saying that you're 82% likely to stay with A, 10% likely to switch to B, and 8% likely to switch to C. If you voted for B last time, then the numbers are just 2%, then 86%, then 12%. And if you voted for C, the numbers are, let's see, switch to A is 14%, 6%, and 80%. It's always fun to make a long-term prediction now at this point, just looking at these numbers. So which political party do you think might benefit long-term? Again, assuming that we're only working with the same 200,000 voters. Okay, if you've made a conjecture, let's go ahead and switch into Matlab Online. Okay, so here we are in Matlab Online. I'm going to fill out my matrix M. We're going to have 0.82. I'm going to go across the first row, 0.02, 0.14, then down to the next row. This is 0.10, 0.86, 0.06. And on the third row, 0.08, 0.12, and 0.80. You can always check yourself by doing sum M, and you should get a row of ones because that adds up the columns of M, and if M is stochastic, that's what you would want to see. Okay, I'm going to say vector B is a vector containing the current voter data. So we've got 80,000 people voted for party A. So that's like saying 80,000 are in state A, 70,000 voted for B, and 50,000 voted for C. Okay, in the next election, we would expect people to move according to M times B. So that's going to redistribute these 200,000 voters according to the probabilities that we've put in the matrix M. Okay, so next election, A is going to win again, but maybe not as decisively. So we've got 74,000 voting for A, 71,200 voting for B, and 54,800 voting for C. That's the next election. What about the election after that? It would be M squared times B. And we can see what those numbers are, but I like switching into format bank just to not have the somewhat unnecessary scientific notation. Okay, so here we go. Now B is winning with 71,920 voters. The election after that, which again, if you're looking at 4-year elections, you would never do this without incorporating new voters and thinking about voters leaving. Okay, but now we can see again, it's B, then A, then C. And if we wanted to do kind of like a long-term prediction, we would say after 3,000 elections, which maybe an election happens every minute, this would be our distribution. So long-term, it actually looks like B is going to win the elections, followed by C, followed by A. Of course, given the context, the exponent 3,000 here is a little silly. Let's just look at that matrix raised to the 3,000th power. And you can see that it's converged. So each column is a vector, which we would call vector U in our notation, showing us that B is ultimately the party that attracts the most voters. Now M here is a positive stochastic matrix because all of the entries are positive. There were no entries of 0. What would it mean to have an entry of 0 in M? Well, it would mean that, let's say this entry right here was 0. I'd have to adjust my other percentages, but let's say that entry in the first column, second row was 0. That would mean that if you voted for A last time, there's no chance you'll vote for B. That's not what we had in this problem. We did have a positive stochastic matrix. In the rest of this lecture, we're going to look at examples where we have zeros, so our matrices aren't necessarily going to be strictly positive. But the good news is that the behavior that we've observed, that if you take a stochastic matrix and raise it to a high power, all of the columns turn into this repeated vector U of kind of long-term predictions. This can happen even if your matrix isn't positive. So what we'll see in this lecture is it's possible for M to contain zeros and still trend long-term if you raise M to a large power to this form where we have the vector U repeated over and over. But we'll also see an example where that doesn't happen, and yet M to the n is still very useful. So in particular, in our last example, when we take our matrix and raise it to a high power, it won't have this form, but it will still give us the long-term behavior. Okay, so let's look at a very simple example and then we'll kind of build up some more complicated examples. Suppose we flip a fair coin, heads and tails. This is a really silly game, but what's going to happen is we're just going to keep flipping until we land on tails. So every time you flip heads, you flip again. If you flip heads, you flip again. But if you flip tails, you stop. So you can imagine this game isn't going to last very long, but let's quantify that. So what's the probability that it would only last one flip? What about two flips? What's the long-term probability? Are we essentially guaranteed that at some point in the future we're going to stop playing this game? What I like to do when I have this kind of problem, especially if it's a little bit more complicated than flipping a coin where there are only two sides, is I like to create a diagram. And sometimes I create one kind of diagram and then I look at it and I say, you know, this diagram could be made more concise. Perhaps I've diagrammed a little bit too much. So you can take a diagram, do kind of a rough draft, and then edit it. So that's what we're going to do now. Let me imagine that I first create the state of starting the game. So you can always do this. You can say, okay, we started. I'm going to put this in a round node like that. What could happen after we start? Well, we flip it, and we're either going to flip heads. So I'll do an arrow up to heads. Or, of course, we flip tails. So I'll do an arrow down to tails. Tails would actually cause us to end the game. So to make my diagram a little bit clearer, what I'm going to do is write that in red for stop, and then I'm also going to do a box. So in my diagram, circle will be a place where you would continue, and a box will be a place where you stop. And then with your arrows, you want to label the probabilities. This is a fair coin, so it's going to be 0.5 for each. Okay, then what happens? Well, if I flipped heads, I would continue flipping. And I'm either going to flip heads again, at which point we would continue, or I'm going to flip tails. So if I flipped heads, we would continue. But I don't want to do this diagram forever. So what I'm going to do is realize that this tails box here, maybe I don't need it because I have a tails box here. And that's like the state of having just flipped tails. So perhaps instead of having this heads go to a brand new box tails, I could draw it down here, at which point we're done with our flipping. From heads to heads, well, we would then flip again so we could keep going heads to heads to heads. Why not just have heads kind of double back on itself? So let me copy this diagram over. Okay, so what we thought of as this arrow right here on the left is now going to be this down arrow here. And I stopped labeling percentages, but we'll bring that back in. And this arrow from heads to heads, it's kind of like the state of having just flipped the heads, so why not just have this box kind of return to itself? Now this picture actually includes the possibility of flipping heads 1,000 times. You would just keep taking this loop from heads back to heads. So this is a very concise way of describing something which actually could go on forever. Okay, let's keep labeling percentages. So from heads, there's a 1/2 chance of flipping tails and a 1/2 chance of flipping heads. Those are going to be numbers that we put into our stochastic matrix. So let me actually start filling that out. Let's think of start as the first column. So it's like box number 1. Heads we'll have as the second. And tails as the third. I'm not actually done with this diagram, but let's kind of see what our matrix starts to look like. From start back to start is not an option. So that first entry in the first column will be 0. But then you could go to heads and you could go to tails. So the first column is 0, 0.5, 0.5. From heads, we don't have a return arrow to start, so that's going to be 0. And then we could keep flipping ahead, so we could flip another one with probability 50%, or we could flip tails. And then from tails, we don't go back to start, we don't go back to heads, because we're not going to flip again, nor do we flip another tails. If I put a 0 down here, this is no longer a stochastic matrix, and I would really like for it to be stochastic. So here's a neat thing that we're going to do. Whenever we have an ending point, like if you flip tails, you're done with the game, no more flipping, we're going to interpret that as meaning that we stay in the tails state forever. So it's equivalent to flipping a tails with 100% probability for the rest of your life. So it's like we flipped a tails and that's our forever state. So for a terminal state, we'll put a 1, indicating that we're not going to move from that state. Okay, so this was like our starting node. This was heads and this was tails. Now this is a stochastic matrix. All of the columns sum to 1, but it's not a positive stochastic matrix because of the presence of all those zeros. Let's see what happens though. Okay, so I'm going to come down into a new cell and we'll just define a brand new matrix. I'll keep calling it M. It's going to be 0, 0, 0 on the first row, 0.5, 0.5, 0, 0.5, 0.5, 1. No reason to do sum here. It's such a basic matrix, but if you wanted to, you could say, what's the sum of all those columns? And as expected, they're all 1. Okay, what's the probability of flipping a tails with 1 flip? Well, that's like start and then flip tails. So that would be first column, third row, and that happens with 50% chance, and that should make sense to you because after 1 flip, there's a 50% chance that you flip to tails. What about after 2 flips? Now it's 75%. So it's like from the start, so we're always going to stay in this first column with this interpretation of the problem. From the start, after 2 iterations, there's a 75% chance that you would have flipped to tails. That actually doesn't mean that the game ended exactly in 2 flips. That means it ended either in 1 flip or 2. You either flipped tails immediately or you flipped heads and then tails. One way to quickly see that 75% or 3/4 is the only way to still be flipping is if you flipped heads and heads, and that would only happen 25% of the time. So 1/2 times 1/2. Okay, so M cubed, the correct interpretation is really how likely are we to finish in either 1, 2, or 3 flips? 88% likely. So there's only a 12% chance that you're going to flip again. If you do, your percentage only goes up to 94%. Okay, so what's the long-term probability? Well, it's 1. It's not too surprising because if you start flipping a coin, you're going to eventually flip a tails. Nobody's going to do this forever. But sometimes people don't like seeing that long-term prediction is 1 because they feel like there is a possibility that you would actually flip heads forever. It is technically possible. So if we want to interpret this a little bit better, let me do format long. Okay, 400 is just too high. Let's do 40. Before I switched formats, M to the 40 would have had a 1 down here, but really it's saying the probability is 99.999%. It's basically converging to 1. So M to the n for any choice of n might not have a 1 down here, but as we let n go to infinity. So if we then take the limit as our exponent goes to infinity, then it does turn into 1. So it's a limit. And then as a last remark here, notice that m to a large power turns into the matrix 0, 0, 1, 0, 0, 1, 0, 0, 1. So even though m wasn't a positive stochastic matrix, we still got the same kind of convergence that we've seen in the past, where we have a column we could call U repeated. What I'm going to do now is re-diagram this problem one more time. So let me copy the diagrams that we already have for comparison. So now let's see if we can take these diagrams and actually make them even simpler with just 2 boxes. So think for a second, is there any way to cut down from 3 boxes to 2? Well, it seems like you would need the heads and you would need the tails, so maybe we can get rid of the starting box. And how I would interpret this is both start and heads mean, okay, flip the coin. So we really have two states here. We're either gonna flip again, or we've stopped because we flipped to tails. So instead of having the starting flip kind of designated with its own box, let's recognize these two conditions as really just saying flip. I'm going to call that heads. So we can say that heads just means, hey, we're going to flip again. And then tails means we're done flipping. Okay, and then we move from the head state to the tails state with probability 0.5. And then we move from the head state back to the head state with probability 0.5. And then since tails state is an ending point, it's like being in that state forever with no variation. So we just stay there with probability 100%. So this diagram captures the feature that the next flip is either going to be heads or tails, and it doesn't really matter back where we started. The only question really that we're asking ourselves at any moment is, do we flip again? In this case, our matrix is only going to have two columns, heads and tails. And it's going to look like 0.5, 0.5, 0, and 1. Okay, so if I take this matrix M here, and let me just edit it, and just get rid of this first column, actually. Like that. That's our new matrix. And let's do just M. And I'll go back to format short. Okay, so there's M, of course, and then M squared. We see that 75% again. So here it's like we're looking at this bottom left number, because that's the state of going from flipping to not flipping. M cubed is 87.5% as we saw before. M to the fourth, 93.75. M to the fifth, 96.88. If I'm trying to solve this problem, either of these diagrams is fine. The first one is too cumbersome to work with, but this one with 3 statuses is okay. This final form is perhaps the best, but there was nothing wrong with having this starting box. So if you're wondering if it was bad, it's not. So if you're trying to diagram an experiment and this is what you end up with, and perhaps it can be made a little bit more concise, it's okay as long as what you're doing is correct. Okay, at this point I want to stop and define what a Markov chain actually is. That's the name of the lecture. It's a stochastic model for a set of states or events, like the state of voting for party A, or the event of flipping a tails, where the probability of any state depends only on the previous state. What that means here is the probability of flipping a heads to a tails doesn't depend on what you did 4 flips ago. So the probabilities don't change even if you accumulate lots of movement. We just say the probability of moving from B to C in this election example is always 12%. It doesn't matter if you got to B from A or from C or something like that. So that's what a Markov chain is. So the first step is usually to diagram your chain. And that can be a multi-step process. You can do several iterations. Perhaps you have an initial diagram where you kind of figure out what's going on. But then you think, well, this could be made a little better. So you make it a little bit better and then perhaps even better again. So you can diagram a couple of times until you really think you have a good picture of what's going on. You identify all the states or the events. So in this diagram on the top right, I have 3 events: starting, having just flipped to heads, having just flipped to tails. In my third picture, I called it heads, but that's really like the state of needing to do another flip. And I called it tails, but that's really like the state of finishing the game. So you want to have a diagram where you have certain states. You have arrows labeling how you can get from one state to the next. And then you label those arrows with the probability of that movement occurring. Then once you have your diagram with your states, the directions of movement, and the probability, You convert it into a stochastic matrix, and then you just hope that a high power will work. If it doesn't, there might be more theory that you want to dig into, but for us, the high powers will always work. I'm just going to bring up the list of steps that I mentioned, look at that for a second, and then we'll go into our next example. Here are the steps that I typically go through whenever I want to solve a Markov chain problem. So the first thing I do is just diagram the situation, even if it's not a very organized flowchart, just kind of want to see how things can unfold. And then it's rare that my first diagram is the best, whether it's because it's sloppy or because it can be better organized, or perhaps I've overcomplicated how many different states I need to have. So then I evaluate the diagram and I say, can it be better? Can it be more concise? So that's a process that you keep practicing until you are able to get a really good handle on what makes these diagrams efficient. Then you want to make sure that you've correctly labeled or numbered the states or events. Each one is going to correspond to a matrix column and also a matrix row. So if you've identified one state as, say, your starting state, you might want to think of that as number 1. And then where you move from that would be the entries in the first column. As you've created your diagram, you probably drew arrows saying how you move from one event to another. Make sure you label those arrows with the associated probability. Don't overlook the possibility that you could stay in the same state. So maybe you don't have to move every time you take an action. So in that case, you might have a loop that kind of doubles back to the same state or event and have that probability associated there too. Those probabilities become the entries in your stochastic matrix. So once I've got my labeled diagram with all the associated probabilities, I build up the matrix. Then typically I would need to go into some sort of computational software like Matlab in order to take that matrix and quickly exponentiate it, because matrix exponentiation by hand is not very fun. So you take your matrix and you raise it to higher and higher powers to see if convergence is happening. And then here's one thing that's really key, and we haven't really identified how to do this yet, but we will in examples where we have perhaps multiple results. And that is figure out which entries in the matrix are actually communicating the information that you're looking for. So if you're looking for the long-term probability of one particular action, where do you find that in the matrix? Okay, let's go through those steps for this problem. You roll a fair dice. If you roll a 6, the game is over, you stop. If you roll 1, 2, 3, 4, 5, you roll again, and you keep doing this until you land on 6. What's the probability of stopping in one move? Within 2 moves, so 1 or 2 moves. Then what's the probability of stopping eventually? So long term, do we expect that we're going to roll this dice forever? Obviously the answer is no, but we'll look at the matrix. Okay, let me do some diagrams here. I'm going to start with a sort of naive diagram, then maybe improve it once or twice. And then once we've got a diagram that we like and we think we can describe efficiently with the matrix, then we'll write down the matrix and then finish the problem in Matlab. Okay, let me just say that, hey, first let's just start. And then from start, I could roll a 1, a 2, a 3. I'm going to run out of room here. So this is a good indication that maybe my diagram could be better. Of course, maybe it can't be. You know, sometimes you do actually model something that's like got tons of states. Okay. 6 is great. That means that we've stopped. So let me go ahead and box this one, like the terminal point for this game. Okay, and then what about 1? Well, we could do a 1 again. So I could keep going with my arrows. That could be the naive diagram where you just actually draw kind of each roll and then you say, well, the next roll and the next roll. But obviously that's going to fill up this page really quickly, and it's also not going to be a diagram that really stops. So instead of doing this, we can say let 1 be the state of having just rolled a 1. Start is the state of starting. 2 will be the state of having just rolled a 2, 3, 4, and 5. Okay, and then from 1, you could roll 1 again. So that would be like a loop back to itself. Or you could roll 2, or you could roll 3, or you could roll a 4. And once again, I have a diagram here. It's going to have a lot of arrows. You might think this would be better done if instead of stacking those numbers up, I did them in kind of a circle and maybe had more room to draw these arrows. But the way I started, we would have one go all the way down here to 6. Okay, and then each of these would have probability 1/6. So would all the starting ones. You can kind of label those. Okay, it's like, wow, this is not a very fun problem because let's just say all of these are 1/6. And then 6 back to itself is actually going to be labeled 1 because that's a stopping point. Okay, so this is not a very efficient diagram, and I'm going to stop here because otherwise it's going to be way too messy. And what you could do is take all of these and draw them maybe in a circle. It just might be cleaner to have arrows kind of diagonally across a circle rather than almost verticals I've drawn here. But now what we're going to do is actually think of a better way to diagram this, which is going to be cleaner. So just like with the coin flipping exercise, we can think of this problem as having two distinct states. We need to roll again, or we just rolled a 6. So let me do roll again. And that's equivalent to having just rolled a 1 through 5. It's also equivalent to starting. Okay, so that's one state. The other one is stop. That's because we just rolled a 6. Okay, what's the probability that we go from the state on the left to the state on the right? So regardless of what we've done, how many times we've rolled, maybe I've rolled the dice 14 times at this point and I only got numbers between 1 and 5. On the next roll, the probability of rolling a 6 is 1/6. That doesn't depend on what I rolled way in the past or how I started. Just at any moment, the probability of moving from the state on the left to the state on the right is 1/6. The probability of staying at the state on the left is 5/6. So we can do like a loop back to itself, and that's 5/6. And then because 6 is the moment where we stop, we never leave that condition. That loops back to itself with probability 1. So now, instead of the diagram on the left, which could have yielded, say, a 7 by 7 matrix, it's going to be 2 by 2. So M is going to be a 2 by 2 matrix that's going to be 5/6, 1/6, 0, 1. Now, had you kept going with this diagram on the left, where you could have had, say, 7 states and all these arrows connecting them, where most of them are labeled 1/6, you would have had a 7 by 7 matrix, but you would still get the right answer. So in this solution, the diagram on the right is not the only correct approach, it's just the most efficient. So let me pull back up Matlab Online. Okay, it's going to be very similar to what we just did, but I'll come down to a new cell. M will be 5/6 and 0 on the first row, 1/6 and 1 on the second row. Of course, those sum to 1 and 1. So if we do M squared, we can see that the probability of rolling a 6 in either one roll or 2 is 30.56%. Within 3 rolls, it goes up to 42.13%. 4 rolls, about 52%. So why am I looking down here? Because this column and this row represent the action of moving from the state, which is in the first column, so that's the state of needing to roll, to the second row, which corresponds to the state on the right, which was rolling a 6. So first column, second row means we moved from the first compartment to the second. Okay, at this point with 4 rolls, we're more than likely to have rolled a 6, 5 rolls, etc. Let me switch to format long. What about if I do, say, 20 rolls? Okay, you can see it's 97.4%, 30 rolls, 99.6%, 40 rolls, 99.9%. So it's converging to 1. If I do 400, it is 1, but that's really just numerically rounding. Okay, here it's kind of funny because it's actually higher than 1, but that's just a numerical issue with Matlab, right? So at that point, you've taken this matrix and raised it to the 300th power. So there's all sorts of kind of numerical issues going on with all these decimals. But the point is, Not that at any moment, like if I do m to the 50, I'm going to get 1, but I'm going to get something that's getting closer and closer to 1. So long term, as that exponent grows to infinity, that number converges to 1. Notice here that even though m was not a positive stochastic matrix, our matrix turned into 0, 1, 0, 1. So the vector u that we've identified in the past is the vector 0, 1. Let's consider this example now, which is going to be an example where there are multiple terminal states. So suppose we're tossing a coin, fair coin just like before, and perhaps we're recording what's happening, and we will stop flipping if we write down HT, so we flip a heads then a tails, HH, or TT. So what is the probability of each of these outcomes? There are 3 possible outcomes. Notice the one we don't see here is TH. So if I do TH, then I would flip again. Okay, I'm going to create a diagram, and as is often the case, the first diagram I draw might not be the best, but let me just start trying to visualize how this coin tossing could happen. Okay, we're going to have a start. We haven't tossed the coin yet. From the start, we're either going to do tails or heads. Neither of those would be terminal states, so let me just circle them. I'll slide this down a bit. Okay, from tails, we would toss again, and we would either get tails or heads. Tails, tails would actually mean that we should stop, so this is like an ending state. Tails, heads, however, is not. So I'll do a circle there. Okay, from heads, I could flip again. I'm still on the top. So this would be like flipping again. And we would either get tails or heads, of course. Heads, tails, and heads, heads are both endings. So I will box them. And I think that takes care of the top branch, so let's go down to the bottom branch. What happens if my first flip is a heads? Then I would either do tails or heads, and again, those would both be endings. Okay, so if I did tails at this point or heads at this point, I would have flipped one of the possible endings. Okay, so here's a diagram. I could start labeling each of these branches with 1/2, but at this point, it's worth taking a second to determine whether or not this diagram is the most efficient, or maybe I want to clean it up, do it a little bit differently. Looking at this, what I observe is that this link here, from tails to heads, at which point I flip again, this kind of triangle I have over here on the right is exactly the same as this one I have down here. So being at this state, this heads right here, and needing to flip again, is really the same as being at this state. So while I could have these separate, it wouldn't lead to the wrong answer. I think it would be better if I took this whole branch here, kind of merged it with this one. So what we're going to do, and I won't erase it, I'll just cross it out. Let me take this whole thing, and I'm going to replace it with a down arrow, sending me from that first tails down to the first heads. Okay, so that's the first thing I'm going to do to this diagram to improve it. I'm also going to change the way I've labeled these terminal boxes, and that's because this tails is not the same result as this tails. This means I did TT, so T and then T. This one means I did HT, and then this one is HH. So actually, since those two box T's are really different, let me just label them a little bit differently so that it's clear which scenario we're looking at for each of these events. So this one is HT, and then this one is HH. I don't see a good way to get rid of that starting block. So if you have something there, that's fine. Sometimes you can get rid of that initial action, and other times you can't, but it's not wrong to have it, so let's just leave it there. Okay, at this point I like my diagram. So if I go back to my steps, we've done the first two. We diagrammed the situation, then we evaluated it, and we found a way to improve it. Now let's go through, and we've already labeled the states, but since we have so many, I'm going to number them as well, and we will also label the arrows with the associated probabilities. Okay, so the start, let's label this 1. So that'll be the first column in our matrix. And then how about 2 and 3? And then 4, 5, and 6. So we're going to have a 6 by 6 matrix. And from the start, you could flip tails or heads with 1/2 probability. And then if you flip tails, you could flip tails again, or you could flip heads, each with a 1/2 probability. And then if you flipped heads down here on the bottom, again, we've got 1/2 probability, or really I should say 50% or 0.5 chance that you would go into boxes 5 or 6. And then I've left off loops here, kind of telling us that once we've stopped, we stay stopped. So each of these gets a loop back to itself with probability 1. I think I'm going to make that branch I've crossed out a little bit lighter because it's distracting me. Okay, so I left that there just so you can see what we started with, but hopefully now it's clear that that's not part of our final diagram. All right, let's make our matrix. It's going to be 6 by 6. And what I'll do is I'll just make the first column and then I'll try to organize it because that's a big matrix. All right, so from block 1, we can go to 2 or 3 and that's it. So we don't go from 1 back to 1, but we do go to 2 and 3, but we don't go to 4, 5, or 6. So that's what the first column in our matrix looks like. Then for the second column, these are all of the ways to leave this state. So we could go to 3 or 4, but none of the others. So we'll have 0.5 and 0.5. And let me just fill in zeros for the rest of the entries. And then from situation number 3, we can go to 5 or 6, but none of the others. That's 0.5, 0.5 down here. Like that. And then 4, 5, and 6 are all endings. So those columns are going to be all 0 except for 1 in each of their respective coordinates. So that's like 1, 1, 1. And then we fill in a whole bunch of zeros. Okay, so there's our stochastic matrix. So we've labeled the arrows, we created the matrix. Now we're going to set this matrix up in Matlab and then evaluate powers of it. And then we'll figure out which of the entries we need to be looking at. Okay, here we are in Matlab. So let's copy in that matrix that we created. The first row is all 0. You never return to that starting block. And then we have 0.5, 1, 2, 3, 4, 5. And then 0.5, 0.5, 0, 0, 0, 0. 0, 0.5, 0, 1, 0, 0. 0, 0, 0.5, 0, 1, 0. And then 0, 0, 0.5, 0, 0, 1. Okay, let's just take a look at that. Make sure it looks right. Okay, I think that looks good. There's no real reason to do it in this example, but you can always sum at that point just to make sure it really is stochastic, and it is. So I will suppress this output. Okay, let's do m squared. You can see the final 3 columns don't change because once you're in those states, you stay in those states, but the numbers in the first 3 columns, which are states where we're moving, those have shifted. And we can cube it, raise it to the 4th power, 5th power, don't see anything changing, let's do 100th power. Looks like we've converged to this form. Unlike before, where we had one column repeated over and over, here we have 6 distinct columns. I'll leave it to you to check that if you were to take the original matrix M and apply it to any one of these columns, so you could call any of these columns, say, vector U, then U would be fixed by the actions of M. So it's like all of these columns are candidates for what we want to study for our long-term behavior. You have to identify which column is the one that's important to you. So what's key here? Well, we started this experiment, so we had to start on the first block. That's how we set up the diagram. And we're interested in, once we start, do we go to block 4, 5, or 6? Those were tails, tails, heads, tails, or heads, heads, respectively. So that information is communicated to us in the first column, because this is from the start, where do you go? And ultimately, after enough time has gone by, from the start, we've settled into either 4, 5, or 6 with these probabilities. If I go back to, say, just m cubed, actually m cubed might already be there. If I go back to m squared, you can see after 2 flips, there's a chance that I'm not yet in a terminal node. I could have flipped tails and then heads, taking me to block 2 and then block 3. But actually, once you've done 3 flips or more, you get convergence. Okay, so once we start this, there's a 25% chance that you'll do tails, tails, and then a 37.5% chance that you'll do heads, tails, and likewise a 37.5% chance that you'll do heads, heads. So that's how we identify which entries in the matrix we're looking for. What does the second column tell us? That's really communicating to us if we start with the tails. So if we write that down first, then what's the probability? And at that point, if you start with tails, if you think about it, your next flip, there's a 50% chance that you're going to flip a tails again, which means that you would finish with tails, tails. So that's what this entry is. So if you start with tails, then there's a 50% chance that you'll end with tails, tails, and then a quarter chance you'll end up with heads, tails, or heads, heads. If you start with heads, the next flip is terminal. You can't go back to nodes 1 or 2. You have to do either heads, tails, or heads, heads at that point, and those happen with 50% chance each. So that's what the first 3 columns communicate to us. They tell us the possibilities of different outcomes based on where we started. The first column with our setup is just your default start. So for any experiment with no prior flipping recorded yet, what's the probability? And then 4, 5, and 6, of course, tell us, well, if you started with tails, tails, you would be done, so you would stay there. That happens at 100% probability. If you started with heads, tails, that would be in the 5th column. If you started with heads, tails, then you wouldn't go anywhere because that's a terminal state. And likewise, if you started with heads, heads, you wouldn't go anywhere. So it's a good exercise to evaluate each of these columns. Make sure you understand what's being communicated. Let's take a look at this example. Suppose 2 cowboys shoot at each other round after round. So they're in some duel, maybe out in the Wild West. Cowboy A shoots with 90% precision. Cowboy B shoots with 70% precision. What's the probability that B is going to win this duel? As is always the case, the first thing I'm going to do is just sketch a picture, a diagram of what's going on, and then we might be able to make it a little bit better. So as I usually do, I'm going to have just a starting block. Okay, we start, and then let's see what could happen. We could have A hits B. We could have B hits A. We could have that they actually hit each other, or they could both miss. Of these 4 blocks, if we're assuming that the duel is over as soon as somebody gets hit, then this one is an ending, as is this one. B hits A and A hits B are both endings, and so is both hit. Both miss means that they're going to go again. So at this point, I could do 4 more arrows, kind of duplicating what we just did. But now you realize that these 4 arrows are going to be the same as these 4 arrows. So both miss and start can be combined. So it's like the start and also both missing, those are really the same status. Both of those are communicating that the duel is about to continue, whereas the other 3 tell you that the duel is stopping. Okay, so new diagram. I'm going to call this first state, I'm going to draw both miss. Doesn't exactly apply for the very first round, but that's okay. It's the same area in the diagram that we're doing. And then from both miss, they could keep missing. So that's one arrow. Let me scoot this over to the right just to distinguish it from the diagram on the left. They could both miss, or at least one could aim correctly. So we could have A hits B, B hits A, or both hit. And then just like before, these three states on the right all mean that the duel is over. Okay, so this new diagram is a lot better than the one on the left. The one on the left, I would have had to keep drawing these forever if I took this route of, taking both miss and then going from there. By realizing that everybody missing is kind of like being at the very beginning of the duel, we're able to take the status of the duel is continuing and roll it all into just one condition. Okay, so let's label these and then label our arrows. Both miss, this will go into our first column, and then we'll have second column, third column, and both getting hit will be the fourth column. Okay, let's do our probabilities. For A hits B, implicit in the way I've labeled this is the fact that B doesn't hit A, because if B did, we would be down in condition 4. So A hits B is really A hits B and B doesn't hit A. So the probability of those two actions happening at the same time is A hits B is 0.9, B doesn't hit A is 1 minus 0.7, 0.3. B hits A but A doesn't hit B is 1 minus 0.9 times 0.7. Both hit is actually 0.9 times 0.7. Both miss is going to be 0.1 times 0.3, or 1 minus 0.9 times 1 minus 0.7. Okay, so those are the probabilities for our matrix. Let's go ahead and make that matrix, and then we'll finish the problem in Matlab. So we have M equals, this is going to be a 4 by 4 matrix. In this case, from that first kind of starting block, we can return to it. So that's going to happen at probability 0.1 times 0.3. That corresponds to this loop over here. We can go from 1 to 2. That's going to happen with probability 0.9 times 0.3. We can go to block 3. That's going to be 0.1 times 0.7. Here's one where I definitely want to sum my column and make sure I've done this correctly, but then 0.9 times 0.7 for going from block 1 to 4. That's really the only interesting column that we have to work out, because the others are all ending states. So we'll have 0, 1, 0, 0 in the second column, 0, 0, 1, 0, and 0, 0, 0, 1. I just realized I didn't label those arrows, but we can do that now. So state 2 loops back to itself with probability 1, as does state 3, as does state 4. Okay, let's finish this in Matlab. So here our first row is 0.1 times 0.3, then 0, 0, 0. Then it's 0.9 times 0.3, 1, 0, 0. 0.1 times 0.7, 0, 1, 0. And then 0.9 times 0.7, 0, 0, 1. Okay, I don't know if those are the right numbers, but they're probably correct. Let's make sure that first column does indeed add up to every possibility. So we sum M and we hope for ones and we get them. Okay, so matrix is good. Just M itself, let's look at this first column. The probability that they're going to have another round is 3%. The probability that A wins and B loses is 27%. The probability that B wins and A loses is 7%. And then lastly, the probability that, I'm not sure how to describe this, both win, both lose, depending on, I guess, if you're an optimist or a pessimist, but the probability that both get shot is 63%. That's after one round. Seems really likely that this is only going to last one round, because the probability that it's going to have a second round is only 3%. But let's see what the long-term behavior is. And of course, we could also lower their accuracy if we wanted it to be a little bit more interesting. So maybe they don't have to shoot with 90% and 70% precision. Say it goes 2 rounds. Probability is adjusted a little bit. If it goes 3 rounds, again, a little bit. Now that first coordinate is 0. It's not going to be actually 0, but it's rounding to 0 to 4 decimal places. Let's do 300. Let's do 3,000. Probably won't see any difference. Okay, at this point, I think we've converged. Of course, if we want to check that, we can take u and make it the first column. So I'm going to set u to be m to the 3,000, and then I'm going to redefine u as its first column, all rows first column. And then let's compare u to m times u. Yep, it looks like u is fixed by the actions of m. So if we go back to just m to the 3,000, or in other words, if we go back to seeing u in that first column, what are we looking at? Well, from the start, or from the condition that the duel is going to continue, we're just going to go to the next round. The probability that A wins is now 27.8%, the probability that B wins is 7.2%, and the probability that they both lose is about 65%. So the probability that B survives is this one. So that's 7.2%. Okay, this was our last example of a Markov chain. I think these problems are really fun, so I hope you enjoy working through them. Thank you for your attention.